Hello everyone. I hope you are all doing good. So today's our topic is electrostatic potential and capacitance. Example 2.6 to 2.7 and NCERT Section 2.9. That is electrostatic of conductors. Disclaimer. The images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. So today's we are going to cover the topics example 2.6 and section of NCERT 2.9, that is electrostatic of conductors, and then example 2.7. Example 2.6. A molecule of substance has a permanent electric dipole moment of magnitude 10 raised to power minus 29 coulomb meter. So there is a substance and the dipole moment of each molecule of this substance has a permanent dipole moment of magnitude 10 raised to power minus 29 coulomb meter. A mole of this substance is polarized at low temperatures by applying a strong electrostatic field of magnitude 10 raised to power 6 volt per meter. So a mole of substance is so 1 mole of this substance is taken and is polarized. What is polarization? Alignment of all the permanent electric dipoles in the direction of electrostatic field. So a mole of this substance is polarized at low temperature by applying a strong electrostatic field. Why low temperature? Because it helps to orient the electric dipole in the direction of strong electrostatic field easily. If the temperature is will be high, then thermal agitations will come into play, which will restrict the orientation of electric dipole moment. So low temperature. By applying a strong electrostatic field of magnitude 10 to the power 6 volt per meter, the direction of the field is suddenly changed by an angle of 60 degree. Now suppose initially the direction of the electric field is horizontal and also the dipole moment is aligned in the direction of all the dipoles aligned in the direction of electrostatic field. So the angle between dipole moment of all the molecules and electric field is 0 initially. Then we change the electric field suddenly by angle of 60 degree. Now estimate the heat released by the substance in aligning its dipoles along the new direction of electric field. Now we want to find how much heat is lost or heat released by the substance in aligning the dipole in the new direction. Now we have changed the direction of electric field by 60 degree. Now these dipoles also tends to change their orientation and tends to align themselves in the direction of electric field to minimize the potential energy. So what is the heat lost? We have to calculate. For simplicity, assume 100% polarization of the sample. So what is 100% polarization? It means all the dipole moments in the substance are aligned in the direction of electrostatic field. This is 100% polarization. So we have to assume that 100% polarization is there. So coming to the solution, dipole moment of one molecule is given 10 raised to the power minus 29 coulomb meter. So as we are taking 1 mole of the substance, so 1 mole of substance contain how much molecules? 6 into 10 raised to the power 23 molecules. So total net dipole moment of all the molecules is P. Net dipole moment is equal to 6 into 10 raised to the power 23 into 10 raised to the power minus 29 coulomb. This is the dipole moment of one molecule and this is the number of molecules in 1 mole of substance, that is Avogadro's number. So net dipole moment of all the molecules comes out to be 6 into 10 raised to the power minus 6 coulomb meter. So now initial potential energy. Initial, which means when electric field is horizontal, also dipole moments are aligned in the direction of electric field. That is initial energy. And formula for potential energy is minus PE cos theta. Potential energy of a dipole. We have calculated yesterday's lecture. So minus PE cos theta. So P is, we calculated 6 into 10 to the power minus 6, and what was the electric field? 10 to the power 6 volt per meter, and since they are aligned in the direction of electric field initially, so the angle between them is 0 degree. So initial potential energy is minus 6 joule. Understood? Now, what is the final potential energy? What is meant by final potential energy? When we change the direction of electric field by 60 degree. So now dipoles are in horizontal position. We change suddenly the direction of electric field. Now the angle between the dipole moments and electric field becomes 60 degree. Now final potential energy is 6 into 10 minus 6 into 10 to the power minus 6, and this is the electric field, and the angle between them now becomes 60 degree. Cos 60 degrees 1 by 2. So it will become minus 3 joule. This is the final potential energy. Now what we want to do now? Now this is the energy minus 3 joule. Initially energy was minus 6 joule, which is less when they were aligned in the direction of electric field. Now the angle between them is 60 degree. Now energy becomes less negative, means energy is absorbed or energy is increased. Now they have to lose this energy to again align in the direction of electric field. That is, dipole tends to align in the new direction of electric field immediately by losing some energy. So what amount of energy they should lose? So firstly we have to find change in potential energy. What is the change in potential energy? Initially it was minus 6 joule and final it was minus 3 joule, and change in energy is 3 joule. That 3 joule is energy absorbed when we suddenly change the direction of electric field. Now the dipoles have to lose this 3 joule energy to again align themselves in the direction of electric field, in the direction of new electric field, means which is the new what is the new direction of electric field? 60 degree angle. So they have to lose 3 joule energy to again align in the new direction of electric field and attain minimum potential energy. So there is a loss in potential energy. This must be energy released by the substance in the form of heat in aligning its dipoles. So this must be the energy that should be released by the substance in the form of heat in aligning its dipole in the new direction of electric field. I hope this is you understood. So if you have any question, then you can ask on that slide itself. So it will be easier to explain this on this slide itself. Now, our next topic, to understand the behavior of electric field and potential inside and around the conductors. Conductor contain mobile charge carriers. Now we know that most of the conductors are metals. So in metals there are free electrons, mobile charge carriers. So in metals there are loosely bound electrons that are valence electrons that are very loosely bound to the nucleus. So we can consider them as free electrons because they are very loosely bound to the nucleus. So these conductors contain mobile charge carriers. In metals, that are electrons. In other, like electrolytic solution, what are the mobile charge carriers? Positive and negative ions. So we are only restricting our discussion to metals only. So it's specifically electrons in metallic conductors. So in metallic conductors, there are valence electrons that are loosely bound to the nucleus. So they are the mobile charges. In metals, valence electrons separate from the atom. So valence electrons are loosely bound. So they separate from the atom and move freely within, but not outside the metal. So in a neutral metal substance, there is equal number of positive and negative charges. So the electron can separate from atom, but cannot leave the metal. It moves freely, but within the metal. So it can move freely within, but not outside the metal, forming a gas-like state. What this phrase means, gas-like state. In gas, we know that molecules are in random motion and they collide with each other. So these electrons forming a gas-like state means they collide with ions and move randomly. So these electrons collide with the ions of the metal and move randomly and also collide with themselves also. So they form a gas-like state. Under an external electric field, they drift against the field direction. We know that if there is any external electric field, the electrons feel electrostatic force in the direction opposite to the electric field. So under an external electric field, they drift against in the opposite direction of the field. So what does drift means? For now we can simply call it move against field direction. But what is drift? Drift is when electron moves, it collides with the ions and also with the other electrons. So after collision, it will gain some acceleration and velocity, and after very small time, it will collide again with another ion or another electron. So it will lose its velocity. Again, it will gain some acceleration and velocity. Again, it collides with any other ion and loses its velocity. So that small portions in which it accelerates or gain velocity, that is called drift. So we will do it in detail in the next chapter, current electricity. So for now, you can simply assume it as move. So they move against the field direction while positive ions remain fixed. Now we know that positive ions are in nucleus. So nucleus doesn't move. Only free electrons that are valence move. Positive ions, nucleus doesn't move, and also the electrons in the inner shells that are very close to the nucleus and that are strongly bound due to the electrostatic force of the nucleus. So they will not move while positive ions remain fixed. Now, key properties of conductor in electrostatics. Inside a conductor, there are 4 key properties. They are very important. So inside a conductor, electrostatic field is 0. That we already know. But why? In static condition, free electrons, free charges distribute themselves to achieve 0 electric field internally. Now in a conductor, we know that in static condition, what is static condition? Static condition is when all the charges are stationary. They are not moving. They are not producing any current. All charges are stationary. So this is in static condition. So in static condition, we know that free charges distribute themselves to achieve 0 electric field internally. Now, if there is external electric field, or we can say there is charge on the surface of conductor, then this charge will redistribute itself in such a way that electric field internally should be 0. Because if there is any electric field exists internally, then this means the free charges will experience some force due to this electric field that is in the internal part of the conductor, due to which that mobile charges move and produce current, which is not the static condition. We are discussing about static conditions. Static condition is when no charges move. There are stationary charges. So for stationary charges, there should not be any electric field in the internal parts of the conductor. To maintain a static conditions, then free charges redistribute themselves to achieve zero electric field internally. At charged conductor surfaces, electrostatic field must be normal to the surface. Okay, now at charged conductors, we have given some charge to the conductor surface. Now electrostatic field must be normal to the surface at every point. Any tangential component would cause surface charge movement. Okay, now electrostatic field should be normal to the surface of the conductor at every point. If it is at some angle other than 90 degree, okay, less than or greater than, it will result in two components. One component is perpendicular to the surface, one component is tangential to the surface. The tangential component will result in the movement of charges on the surface, which is not required because we are dealing with static conditions, static charges, electrostatic. So if there is a tangential component of electric field, then there will be movement of charges on the surface and there will be current. So in stationary condition, when charges are not moving, the tangential component of electric field should be or must be zero. So there should only be perpendicular component of electrostatic field on the surface of charge conductor. So that's why electrostatic in stationary conditions at charge conductor surfaces, electrostatic field must be normal to the surface at every point. Any tangential component will cause surface charge movement. Excess charges resides only on conductor surfaces in static conditions using Gauss law. Okay, excess charges that we are giving any excess charge to any conductor, it will reside only on surface of the conductor. Why? We will also see the reason. But first, excess charge resides only on the conductor surfaces in static conditions. Static condition you should also mention. So why charge only resides on the surface of the conductor? Because according to Gauss law, firstly we know that electrostatic field inside the charges inside the conductor is zero. So there is no electrostatic field inside the conductor. So using Gauss law, what is Gauss law? Gauss law is electric flux through any enclosed surface is equal to the charge enclosed by that surface upon epsilon naught. Okay, so if we want to find the electric flux through any enclosed surface, which is equal to charge enclosed by that surface upon epsilon naught. Now we know that inside the conductor there is no electrostatic field present. So if we take any small volume inside the conductor, you can assume that if a very big sphere is there, we can assume a small volume inside that sphere and enclosed surface, very small sphere in that bigger sphere, and this sphere, small sphere, has enclosed surface. So since there is no electrostatic field present inside the conductor, there will not be any electric flux through that small volume element that we have taken. So electric flux through that small element will be zero, which means according to Gauss law, there is no charge enclosed by that surface. That means if there is no electrostatic field present inside the conductor, there should not be any charge inside that enclosed surface of volume element. Okay, So using Gauss law, for any volume element inside a conductor, the total electric flux is zero through that surface because electrostatic field doesn't exist inside the conductor, indicating no net internal charge. This means there is no net internal charge. So that excess charge we are giving to the conductor should only resides on the surface of the conductor to maintain the static conditions and to maintain the electrostatic field zero inside. Electrostatic potential remains constant throughout conductor volume and surface. No work is done. Electrostatic potential remains constant throughout the conductor and volume and surface. No work is done moving test charges within or on the surface since E is equal to 0 inside and has no tangential component, surface component. Okay, we know that if electrostatic field is 0 somewhere, then if we want to move any charge inside the conductor, there is no electrostatic field present inside the conductor. So if we want to move any charge inside the conductor, we have to do no work because there is no electrostatic field present. There will not be any force on that charge particle. We don't have to do any work against that force because there is no force exist inside that conductor. So we don't have to do work against any force. So moving a charge inside the conductor requires no work. So if no work is done moving test charge within or on the surface, then what it means, work is equal to charge into potential difference. So if work is 0, this means potential difference is also 0 inside any 2 points in the conductor. So potential difference between 2 points inside the conductor is also 0. This means the potential is constant at every point inside the conductor and also on the surface. Okay, since E is equal to 0 inside, why no work is done? No work is done moving test charge within or on the surface since E is equal to 0 inside and has no tangential surface component. There is no tangential surface component present, which will result in force on the charge particles that are on surface. So in static condition, moving a charge from one point to another point inside or on the surface of conductor requires no work. Hence, there is no potential difference, which results in constant potential inside or on the surface of the conductor. So electrostatic potential remains constant throughout the conductor volume and surface. So this can also be done in this way that we know that what is the relation between potential and electric field. Electric field is equal to minus dV by dr. So if electric field is 0 inside, so dV by dr is equal to 0. If derivative of any physical quantity is equal to 0, this means that physical quantity is constant. So dV by dr is 0, which means V is constant throughout the volume of the conductor and on the surface. I hope you understood. Okay, another key property, electric field at charge surface is equal to sigma by epsilon naught n cap. So this is the value we know that when we have done Gauss law, then we came to know that electric field due to surface, any sheet or surface, plane surface, that is sigma by epsilon naught. Sigma is surface charge density, Q upon area, and epsilon naught is constant. And that n cap, where sigma is surface charge density and n cap is outward normal unit vector. Okay. Okay, this is the diagrammatical representation. Now we will deduce this term from this diagram. Now assume or take any small surface that we also known as pillbox. Pillbox is small cylindrical surface that enclose some volume. So this is the small cylindrical block which is known as pillbox. So this pillbox is partially inside the surface or partially outside the surface, and this surface is charged, and surface charge density of this surface is sigma. So this is the pillbox partially inside. So inside the conductor there is no electrostatic field. Outside there is electrostatic field due to this surface charge density, and electric field is in the outward direction due to these positive charges. If this surface charge density is due to negative charges, electric field will be in opposite direction. Okay, so now there is some electric flux through this pillbox surface. Now this is partly inside. If we place any enclosed surface inside a electric field, the flux through it is zero, because electric field are entering and exiting that same surface, and the inward flux is equal to outward flux. But here this pillbox is partially inside, and inside there is no electric field, and outside there is electric field. So electric field is only exiting this surface, not entering anywhere. So there is some net flux through this surface. Net flux through this surface. Delta S is the area of this small circular section of this pillbox surface. This is the electric field and this is the surface charge density sigma. Okay, what is figure showing? The Gaussian surface, a pillbox chosen to derive equation for electric field at the surface of the charge conductors using Gauss law. Now applying Gauss law, which is electric flux, which is E into electric field into area. So E into delta S equal to charge upon epsilon naught. So what is the charge of this surface? Sigma, that is surface charge density, into area of this small circular section. This is the charge enclosed by this pillbox upon epsilon naught. So this is the Gauss law. So delta S will cancel out and result in E is equal to sigma by epsilon naught. This is the same result. Why we applied mod here? Because this sigma can be negative if there are negative charges here. So electric field direction will be reversed. Electric field will be in inward direction if there will be negative charge. Key properties of conductors in electrostatic. Electrostatic shielding, that is very important topic from the point of view of next chapters, capacitor and capacitance. So what is electrostatic shielding? Electric field inside a conductor cavity is zero. So we also discussed that electric field inside the conductor is zero, and if there is any cavity inside the conductor, then electric field inside that cavity is also zero. So what is cavity? That we means suppose a ball or football. There is a surface thickness and inside it is cavity. So cavity can be large, small, or of any size, and the cavity, regardless of cavity shape, conductor charge or external fields. Electric field inside a conductor cavity is always zero, regardless of its shape, conductor charge or external fields. Doesn't matter. Cavity shape doesn't matter. Conductor charge doesn't matter, or external fields also doesn't matter. It is always zero. So all charges resides on the outer surface of the conductor. We know that from the key properties that all charges resides on the outer surface of the conductor. This principle enables protection of sensitive instruments from external electrical appliances, from external electrical influences. Okay, this is the diagrammatic representation of a cavity. So this is cavity. This is cavity. This is the charge distribution on the surface of this conductor. This is a conductor of irregular shape, and this is cavity also not of any shape, regardless of any shape. This can be of any shape, any regular shape, any regular shape. Okay, so this is charges on this conductor redistributed itself. So if we apply the electric field in this direction, then electron will experience force in the opposite direction of this electric field. So electron will accumulate in this side and positive charge will accumulate in the direction of electric field in this side. So they will distribute themselves on the surface of this conductor in such a way that electric field inside this cavity will become zero. So if there are positive charges here, there are negative charges here, there is some electric field that will set up inside this cavity in this direction, positive to negative. We know that electric field, direction of electric field is positive to negative. This is external electric field. This is the internal. So internal electric field is in such a way that it is always equal and opposite for conductors only, because there are much amount of free charges present in the conductors. So these charges can produce same amount of same amount of electric field as that of external electric field. So that electric field that is induced due to charge distribution on the surface of this conductors, so this will cancel out the effect of external electric field and electric field inside the cavity will become zero. And there are also not any single charge in this cavity. Charges are on the surface. So surface charge density is also zero. Surface charge density is also zero inside the cavity. Electric field is also zero inside the cavity. But potential is equal to V naught. V naught is any constant value. It can vary from cavity to cavity or shape of the cavity or any other factors. So constant value can vary, but it will remain constant throughout the conductor and on the surface. So this is the negative charge. So surface charge density is less than 0, surface charge density less than 0, surface charge density greater than 0, surface charge density greater than 0. So the electric field inside a cavity of any conductor is 0. All charges resides only on outer surface of a conductor with cavity. There are no charges placed in the cavity. Now, other thing we have mentioned here, this principle enables protection of sensitive instruments from the external electric influence. Since because of electrostatic shielding, there is no electric field present inside this cavity. So we can prevent or protect the sensitive instruments that are used in various electronic devices that are very sensitive to external electrostatic field. That external electric field will interrupt their working. So to protect them, for their protection, we will place these instruments inside this type of cavities. And this cavities will prevent them from the external electrical influences. These type of cavities and this type of configuration also known as Faraday cages. So these are Faraday cages that are used to protect sensitive instruments from the external electrical influences. So figure 2.19 gives the summary of the important electrostatic properties of a conductor that we discussed. All the properties, they are summarized here. So electric field is 0 inside the conductor, volume charge density is 0, no charge present inside the volume of the conductor, and electric field is also 0 throughout the volume. And this is okay. If electric field is 0, then potential is constant inside and also on the surface, that we also discussed. Why? Because there is no electrostatic field present inside here, so there is no work. There is no work required to move a charge from any 2 points between this inside this conductor. So potential is constant everywhere. On the surface, electric field is perpendicular to the surface. There is no tangential component present, so there is no force on the charges on the surface. So also no work required to move any charge on the surface also. So potential is also constant on the surface. Again, this is the conductor. So this is positive charges, these are negative charges. So this surface charge density is greater than 0, surface charge density less than 0. So these charges distribute on the surface of conductor in such a way that the electric field in the internal parts of the conductor will become 0. And outside, this is sigma by epsilon naught. And this one, cavity, electrostatic shielding. Again summarizing, if there is an electric field outside external electric field, it will result in opposite force on the electrons. Electron will shift towards this side and positive charge will accumulate on this side. So this will result in internal electric field, and this internal electric field is equal to external electric field and will cancel the effect inside this cavity, and electric field becomes 0 inside the cavity. Also surface charge density is 0 inside the cavity because there is no charge present. Figure 2.19, some important electrostatic properties of a conductor. Also there was a precaution regarding lightning or thunderstorm. It was told that during lightning or thunderstorm, if you are in a car or any enclosed configuration like car or any vehicle, you should remain in that, not two-wheeler, in four-wheeler that is enclosed. So you should remain in that vehicle, because if lightning strikes that vehicle also, you will not get harmed, because that will behave as Faraday cage and do electrostatic shielding. So when lightning strikes, the electric field inside the cavity, that inside portion of the car is cavity, and car is made of metal which is conductor. So charges will redistribute and cancel the effect of external electric field inside. So inside the electric field will remain 0. So you will not get harmed even if the lightning strikes a vehicle, unless and until you don't touch any of the objects in the car, or any don't touch the surface of the car. Okay, there is example 2.7. A comb run through one's dry hair attracts small bits of paper. Why? What happens if the hair is wet or if it is a rainy day? Remember, a paper does not conduct electricity. So a comb run through one's dry hair. This is something you used to call magic in childhood, that we run the comb or scale in the dry hair and then attract the small bits of paper. Then we call it magic. So what is the physics behind it? So attract small bits of paper. Okay, this is the first question. Then what happens if the hair is wet or if it is a rainy day? Remember, a paper does not conduct electricity. Paper is a insulator. So this is because the comb gets charged by friction. So when we rub scale or a comb in the dry hair, due to the friction between the scale and the dry hair, molecules in the paper get polarized. Okay, due to which some charge will appears on the scale. It depends upon whether the electrons are transferred from scale to here or here to scale. So polarity of charge will depend, but it induces charge due to friction on the comb. When this comb is placed very near to the papers, so paper get polarized, means there is charge distribution or alignment of moments. We will do polarization in detail in next lecture. So paper get polarized, due to which charge appear on the surface of paper due to induction. That method is called induction. You have also studied in this chapter in the starting, producing charge during induction method. So this is induction of charges. So charges present on comb induces charges on paper and resulting in the net force of attraction between comb and paper. So this comb will attract the paper towards it. Okay. So what happens if the hair is wet or if it is a rainy day? So in rainy day, or can say hair is wet. So when we rub comb or scale, then due to the water present in the air, friction will reduce. So friction between the hair and the comb reduces, which will result in that comb does not get charge or get very small amount of charge that is not enough to attract the bits of paper. So comb does not get charge due to friction reduction, and thus it will not attract small bits of paper. Next, B part. Ordinary rubber is an insulator, but special rubber tires of aircraft are made slightly conducting. Why is this necessary? So ordinary rubber is insulator. Ordinary tires are also insulator, but tires of aircraft are made slightly conducting. Why is it? And the C part is vehicles carrying inflammable materials usually have metallic ropes. That vehicles that contain inflammable materials, there is a rope attached with the vehicle and that rope is touching the ground. Metallic rope. Why? So let's see the reason. To enable them to conduct charges produced by the friction to the ground, as too much of static electricity accumulated may result in spark and result in fire. We know that when during takeoff or landing, aircraft is in very high speed. So that tire, when it touches the ground and when aircraft moves in very high speed, there will be very large amount of friction. Due to friction, there may be charge induction, na? There will be charge accumulation. Static electricity means static charges start accumulating on the tire. So large amount of static electricity can result in spark production and results in fire. So to avoid that thing, that rubber tires of aircraft are made slightly conducting so that the large amount of static electricity that is accumulated will go in the ground, will dump into the ground. So accumulation of charges is hence reduced to avoid the spark or fire conditions. And the reason for C is also same. When there is a inflammable materials in the vehicle, so then metallic ropes. So due to the movement of vehicle and friction between that material inside, there will be static electricity generation. So due to static electricity, the inflammable material can catch fire due to spark. So to reduce the accumulation of these charges on these inflammable materials, a metallic rope touching the ground is introduced, so that extra charges that are accumulated will go in the ground. That is also called earthing. The dumping of extra charges in the ground. So D part, a bird perches on a bare high power line. This is very common question. So when you see that bird can sit on the high voltage power line, but you cannot touch it and nothing happens to the bird. A man standing on the ground touches the same line and gets a fatal shock. Why? So solution is, current passes only when there is a potential difference. Okay. So when you touches the wire and your hand is on the wire is on high potential, high voltage power line. So your hand is on high voltage. Your feet are on ground. A man standing on the ground now. So man's feet is on ground. So potential of ground is considered to be 0. So there is potential difference between your hand and feet. So if there is potential difference, current starts to flow through your body. High current starts to flow through your body. This will result in fatal shock. But when bird sits on the high voltage power line, it is not in the contact of ground. So both the feet of the bird are on same power line. So the potential difference between the feet of the bird is 0. So there is no flow of charge through the body of the bird. But if the bird will touch the another power line, it will get a shock. You may have seen that if bird's wing or any body part will touch the another wire, then this will result in shock to the bird also. But to a single power line, it will not result into the shock. So this is all about today's topic. I hope you enjoyed the session. Thank you.